The second derivative test is a test for determining local extrema of a function. But so far, the way we've been able to determine local extrema for a function, that is local maxes and mins, it only used the first derivative. The first derivative, we got the critical points by finding where the derivative was 0 or undefined. And then to determine if any of those critical points were local maxes or mins, we had to look around the critical points and see what was happening to the first derivative on either side. The second derivative test still needs the critical points from the first derivative, but it utilizes the second derivative information to help us make our determination about maxes and mins. So here's the deal. If f double prime is positive, we know that means that the original function f is concave up. So if the original function f is concave up, we see a minimum place right there. So we're able to conclude that we would have a local min, but it would have to be at a critical point. And then likewise, if we have the second derivative being negative, that would mean that the original function f is going to be concave down. Concave down looks like this, and we visualize a local max this time. But again, a max can only happen at a critical point, so we would have to be looking at a critical point to begin with. And the important thing here is a lot of times students think positive means big and big would mean max, but that's really not what's happening here. Positive for the second derivative that we would be seeing here gives us a local min, which perhaps is counterintuitive unless you really think about what it means to be concave up, which is what we really are associating with positive. So it's really important to go through this middle mental exercise of getting a visual of the function and what it looks like to be concave up to see the min, and what it would look like to be concave down so that you can see the max. And so what we're going to do is demonstrate this second derivative test by an example. So we want to use the second derivative test to determine the local extrema, that is local maxes and mins, of f. And here's our function. F of x is x squared times x minus 1 times x plus 1. Now it's in factored form, but factored form of f is actually not very helpful. And so we really need to go ahead and multiply it out so that we can easily take the derivative. So we have x squared, and then the x minus 1, x plus 1 is the factorization of the difference of squares, x squared minus 1. So that multiplies out so far. And then we can distribute the x squared to get x to the fourth minus x squared. Okay? And that's just f of x. So we're ready at this point to take the first derivative using the power rule for each term. We've got 4x cubed minus 2x. And we could take the derivative again because we're trying to utilize the second derivative test. And so, again, it's a polynomial, so we can take it term by term using a power rule. So we've got 12x squared this time minus 2. And we need both of those derivatives because we're going to use the first derivative to get critical points as our candidates for local maxes and mins. And then we're going to test those critical points in the second derivative to determine if we do in fact have a max or a min, or it's possible that the second derivative test is inconclusive. And so let's go through those steps. First step is we need to find the critical points. So we'll say critical points, and what we're looking there is f prime equal to 0 or undefined. Just like we had found critical points before as our candidates, they're still our candidates for maxes and mins. So our critical points are where the first derivative is 0 or undefined. Well, we have f prime of x here but not in factored form. So let's go ahead and factor it. We've got the greatest common factor of the two terms is the 2x, leaving us with 2x squared minus 1 as the remaining part of the factor. So if we're looking at where is f prime equal to 0, we're just setting each factor equal to 0 and solving. So the first factor equal to 0 gives us x equals 0, and the second factor equal to 0 gives us x squared equals, if we add over the 1, divide by 2, we have 1/2, which gives us x is equal to plus or minus, when we take the square root of both sides, square root of 1/2. We can simplify this by taking the square root of the top and the bottom, which would be, we'd have plus or minus 1 over root 2, and then rationalizing that, that'd be plus or minus root 2 over 2. And so those are our 3 critical points. And now we need to take those 3 critical points and test them in the second derivative. So we plug critical points into f double prime. That's our next step here. Okay. I guess I forgot to mention that f prime is never undefined, because it's a polynomial. And so critical points could be where f prime is undefined, but it's not ever undefined there. Okay. So we do, in fact, have 3 critical points. We're going to plug them each into f double prime. And so f double prime of 0 is going to be the 12 times 0 squared minus 2. The big deal is that it's negative. We don't really care about exactly what the value is, but the big deal is that it's negative. Negative to us means concave down, and we see a max there. Now, when we're looking at f double prime of either the positive or the negative root 2 over 2, it doesn't really matter that we don't have to do them separate, because the only place f double prime has an x is when it's squared. And so whether it's positive or negative, we're going to get the same result. So I'm going to go ahead and just plug these in together, because that would be 12 times either plus or minus root 2 over 2. We're going to take that and square it, and we're going to subtract 2. And we remember here that the root 2 over 2 is really the square root of 1/2. And so then we're going to square that. So it's really 12 times positive 1/2 minus 2. So that would be 12 times 1/2 would be like 12 divided by 2. So it would be 6 minus 2. Overall, then that's going to be a positive value, positive 4. And so we see if it's positive, we see concave up, and it's a min. And so what we conclude is that we have a local max at x equals 0, and we have a local min at x equals both plus and minus root 2 over 2. And those would be our 3 extrema. And we got those from the second derivative test by finding critical points using the first derivative and then testing them into the second derivative to utilize the idea of concavity to visualize a max or a min for each.